Hi guys, so what we'll look at next is CPU modes. Now, although we learned that the core of the CPU is the kernel, there are multiple other layers to this, and that's where the topic CPU modes come in. CPU can exist in one of two different modes, right? The first mode being the kernel mode and the other mode being the user mode. The kernel mode is sort of at the center of this operating system architecture, which is considered to have the most privileges. What I mean by privileges are the ability to access RAM unconditionally. Anywhere in the RAM it can access. It can access I/O unconditionally. It can access the processor unconditionally. A lot of hardware resources can be unconditionally accessed, unrestricted, for any devices in the kernel mode. In the user mode, however, it's sort of the outermost least privileged ring. It can still access the RAM and the processor and the I/O, but not at a level as unrestricted as the kernel. So you can think of the kernel mode applications sort of like the bosses, whereas the user mode applications are sort of like, employees that don't have access to company property as much as the boss does. So kernel mode is the unrestricted mode of any CPU where executing code has complete and unrestricted access to the underlying hardware. So basically this is the layer in which the operating system and the respective device management, memory management processors run. It can execute any CPU instruction and reference any memory address. That's how powerful it is. So stuff like the operating system can access any memory address and can execute any CPU instruction. However, the user mode is where all and most of the applications that we use run. Google Chrome, all of that stuff, they run on the user mode, which is a restricted mode where the executing code has no ability to directly access hardware or reference memory. They can indirectly access the both, but they can't directly access it like the kernel. So we say that in the user mode, applications are given something called a virtual address space, which means that that application has a separate sort of virtual RAM for it, and that application only sees that portion of the RAM, which is called the virtual address space. Other portions of the RAM cannot be accessed to by that application, and neither can any other application access this application's virtual address space. That's sort of what benefit user mode brings. Code running in user mode must delegate to system APIs to access hardware or memory. So since these applications can't access any of the system's resources themselves, they should use something called system APIs, which are systems application programming interfaces to access respective hardware and memory. So kernel mode unrestricted, user mode restricted. Moving on. Now, once that is out of the way, we'll look at interrupt handling. Now, interrupt handling is something that we've already looked at for the most part in AS. So we'll go through this in summary now. An interrupt basically is when the CPU checks if something has gone wrong and tries to fix it. So it could be you pressing Control or Delete, plugging in a USB, hardware failure, software failure, whatever. It's something that happens externally or internally that impacts whatever process is currently being executed. So in interrupt handling, the CPU constantly checks for interrupt signals. Basically, interrupt signals are signals that are sent by other sources that are trying to get the CPU's attention, and how it does this is by setting the interrupt flag to true. An interrupt flag is a particular flag inside a register inside the CPU that can either contain 1 or 0 most of the time, where 1 means that the interrupt flag is set or interrupt signal was received. When an interrupt is received, the CPU will enter into kernel mode. If you remember from the last discussion, this means that the CPU now has unrestricted access to the computer's resources. And as a result, what will happen is, once the interrupt is received, the CPU will consult something called the interrupt dispatch table. Now we'll understand what the dispatch table is soon. For now, we'll keep it out of the door. We'll not worry about that right now. Now, moving on from what we learned in AS, interrupts have three main sources as far as A2 is concerned. An interrupt can happen from a device. Maybe your printer is out of paper, or you're trying to use a keyboard that is not plugged in. Those can also result in device-based interrupts. Exceptions are software errors. Basically, when you try to divide a number by 0, when you try to execute an instruction that the CPU doesn't understand, when you run into something called a stack fault, those are software-based errors which might also cause interrupts. And then there are things called traps, which are softwares not undergoing errors, but softwares requiring attention besides their normal process. So let's say, like in a Chrome application, there's a sudden alert, right? The Chrome application was doing what it was supposed to do, but suddenly there's an alert. That could be an example of a trap. So for example, a process while doing its task suddenly requests the disk drive. For example, you might be installing an application. It is installing off of the first CD, and then once the first CD installation is over, it might be asking you to enter or put in a second CD. So those are software based interrupts, not errors, but software requesting additional support from the CPU. Now we'll go back to the interrupt dispatch table. Now let's read this first and understand that the IDT, or interrupt dispatch table, is a data structure which is used to relate device descriptors with interrupt routines. The IDT is used to create something called an interrupt vector table, IVT, which is a data structure that associates a list of interrupt routines with a list of interrupt requests. The IDT is indexed by the device descriptor. This is then used to access the appropriate IDT entry and call the low-level interrupt routine. Now, we'll understand what on earth this entire jargon meant. Let's say that you plug in a printer. When a USB device such as a printer is plugged in, there might be an interrupt that is sent to your CPU. An interrupt is sent to the CPU from the printer. Specifically, the I/O management processes will notify the CPU that you plugged in a USB printer. Now, the CPU gets the signal, but it needs to identify the source of the interrupt. So the idea is the source of the interrupt here is the printer, right? The CPU receives the interrupt, but the CPU then tries to identify who sent me this interrupt, and it does that by figuring out what device sent the interrupt, which in turn in this case is the printer. Now the printer might have some descriptor, a sort of unique name. This might be HP Inkjet 01. This is called the device descriptor. Now when the device is plugged in, remember there is something called the IDT. This table has a list of possible devices that can be plugged in, and when it's plugged in, what the CPU should do. Basically, what is the routine or subprogram to run when the printer is plugged in. So there is probably like one row in this interrupt dispatch table that says HP Inkjet 001 should run this program when plugged in. That's what it means to relate device descriptors with interrupt routines. Device descriptors are sort of names of devices that are causing these interrupts. Now it can be a device or a software or whatever, right? Here it says device because devices are mainly the source of interrupts, but it could be anything. And that is paired up with an interrupt routine, which is an address of another program that needs to be run to process this printer plugin, which is the interrupt routine. Now once that is done, you need to send a request to the CPU saying, okay, you need to run this interrupt routine now, right? And once this interrupt routine request is sent, the CPU will then run the low level interrupt routine. So basically, if you think about the IDT contains relations between device descriptors and interrupt routines, which are like this name of the printer and the respective program it should run to understand that USB plugin. Because I mean, the interrupt service routine dispatch table doesn't have all the information. The interrupt dispatch table just contains devices and what should be done when that device is plugged in, or whatever other interrupt. So here in this case, when the device is plugged in, there's a program which is pointed to by the IDT, which probably lives in the RAM or hard disk drive. And what the CPU will do is the CPU will receive this interrupt request and then will go and run it. And by running it, the CPU can then finally solve that interrupt. So here running this means to actually understand that this printer was plugged in and load the respective device driver. That's the idea, guys. So interrupt dispatch table is basically a data structure that relates device descriptors with interrupt routines. Now, what we learned in AS is that interrupts have something called priority levels, right? Certain interrupts are more important than others. Now we are in A2, we are learning about these interrupt priority levels in a lot more detail. Interrupts can be prioritized based on interrupt priority levels, or IPLs, not the Indian Premier League, but the interrupt priority level is what we discuss here. A process is suspended only if its interrupt priority level is greater than that of the current task. So the idea here, guys, is if there is an interrupt that comes into the CPU will only take it in if the priority of the incoming interrupt is higher than that of the current task. So the process with the lower IPL, if there's some process that has a lower priority, then that priority process goes and saves itself in the interrupt register and is handled when the IPL value falls to a certain level. What exactly does that mean? Now, here there are two processes that are competing for the CPU's attention. One process is requiring the interrupt and there's another process that is currently being taking place, right? So the idea is the process with the lower interrupt priority level is saved in the interrupt register and serviced when the IPL value falls to a certain level. So what that means is there is a certain interrupt priority level that the CPU might currently contain, but when at that level only interrupts that have a level higher than that can be serviced. But then what happens if lower level priority interrupts come along? Then they'll never be serviced, right? So what happens is gradually the CPU will reduce the interrupt levels, and what happens is when a lower level interrupt is arriving, it will be momentarily saved in the interrupt register and it will be serviced only when the interrupt level falls back to the level below that current interrupt. Now there are multiple interrupt levels. For most systems it ranges from value 0 to 31, right? 31 is like the highest interrupt level. So 31 is power fail interrupts, 24 is clock interrupts, 20 to 23 is IO devices, and then 0 is for normal processors. So normal processors also have an interrupt level. That's what we mean when we say a process is only suspended if its priority level is greater than that of the current task. So normal processors are always 0. So any interrupt that comes along is greater than the current level. So therefore normal processors can be interrupted. So in case another process that has a high level interrupt comes along, then this interrupt is sort of serviced while the current process is sort of saved so that it can be restored once the interrupt is serviced. We'll understand the interrupt process in a small diagram. Now this diagram is the most important. Now if the previous part was a bit too difficult for you to understand, this diagram is the most important you should understand. First we look at the interrupt process. In the interrupt process, the interrupt is received. That's the first thing that happens. And interrupts with lower priority are disabled to prevent those interrupts from getting interrupted again. So lower priority interrupts are, other priority interrupts, meaning if there's an interrupt that is coming into the CPU, interrupts that are of higher level than the current interrupt that was taken in by the CPU is disabled. So interrupt is received, other interrupts are disabled. You can think about it that way. So that the current interrupt doesn't get interrupted again, there will be another problem. After that, the state of the current process is restored. What I mean by restored is saved so that it can be restored after the interrupt is complete. Restoring here means to save it into the process control block, or that process control block goes and saves itself in a place called the kernel stack. So interrupt is received, other priority interrupts are disabled, and the state of the current process is restored. Then the interrupt source is identified, whether it's a device interrupt, exception or trap, and where the interrupt was created from. Then it jumps to the interrupt service routine based on the interrupt dispatch table. Remember the device descriptors and routines. It finds where the device is, jumps to that routine, and then it services it. Once it is serviced, the process that was interrupted at the beginning, this guy, that guy is restored from the kernel stack. And then the serviced interrupt is restored and other interrupts are re-enabled so that they can be handled. Right, so that's it for this video. In the next videos, we'll look at memory management, specifically paging and segmentation. Bye-bye.